Okay, so hope am I audible? Let me share my screen first. Yeah, so today we'll, so hope my screen is visible, right? All right, so today we'll discuss basically yeah, so we use Mathematica for solving and visualizing dynamical systems, and we discuss the numerical techniques for solving ordinary differential equations ODEs and many systems in nature, for example like the coupling so the cooling of a cup of coffee and the motions of a double pendulum. So, do not have simple analytical solutions, we have to solve numerically, right, and visualize their phase space, okay, in Mathematica. So, how to do that? So, let first discuss the Euler methods, okay, that is to solve the ODEs, the ordinary differential equations, right, and this is the linear approximations. Okay, why I am saying this is a linear approximations? Okay, so it's become clear in a minute. So, okay, so before I starting into this, so you have any questions from the next class or from the previous class? Sorry. Or weak content in the portal? Okay, so if not, so then I'll start. Okay, at yeah. As in the meantime, if you have any questions, okay, so please stop me and ask your questions. So, let us first discuss the Euler method. So, the core idea of numerical method for an ODE to solve the ordinary differential equations. So, basically, so this is the first order equation. So, I just wrote, so dy dt equals to sub functions of y and t, right. So, this is some functions of y I and t, this is the right hand side, and we have only one derivatives, right, and we have to solve this. So, is to approximate the next value y n plus 1 using the current value y n and the small time step h. Okay. So, this is the approximate solutions of an ODE. So, we take a linear approximations where if you know the current value y n, let us say n equals to 0, and then we update y 1 using this formula. Okay. So, this is basically in the Taylor series expansion the first up to the first order term, okay, you take. So, that is why this is a linear. So, I ignore a square term in this series. Okay. And your time step t n plus 1 is basically t n plus h. So, this is basically slope is constant. Okay. So, throughout I constant the slope and it's update one by one using this linear approximation. So, let us apply to this Newton's law of cooling. Okay. So, the rate of change of temperature T of an object, let us follow these equations, okay, according to this Newton's law of cooling. So, the equations again is the first order equations, okay, where you see that the d t capital T over d small t. So, small t is time and capital T is the temperature. So, which is proportional to T minus T environment, where the T environment is basically the ambient temperatures and T is the actual temperatures, okay, the real temperatures. Okay. And this proportionality constant equal minus k, where k is greater than 0, right. So, this is according to the Newton's law of cooling. Okay. So, these equations, and we know that what is the exact solutions, right. So, this is the first order equation. So, you just easily solve. So, your exact solutions is basically T minus T environment is proportional to e to the power minus k t, and then you just write that. So, once you put the initial conditions, so at t equals to 0, this is T naught, and t equals to T naught. So, at t equals to 0, you can check. So, at if you put t equals to 0 here, so this e to the power minus k t is 1, and then the T environment is cancelled. So, your T equals to T naught, right. So, this is basically your T naught is basically your initial temperature at t equals to 0, and at any time t. So, this is the solutions, okay, the exact solutions of these equations. Okay. So, now we test this via numerical method, right. So, first we calculate this using Euler method, the first order approximations, okay, the linear approximations, okay, because we kept only h to the power 1, that is why, okay, and we ignore all a square terms, the non-linear things. Okay. So, we test this via numerical method, and first we assign the values of the constant. So, here k is a constant. So, I put some number 0.3, and your ambient temperatures I set 25, okay, and T naught is basically I set 90. Okay. So, if I run this, okay, so I assigned this number to these variables, okay, and now I define the function. So, you see, so my standard form is this. So, dy dt equals to f of y t. So, in this case your y is basically temperature capital T, and the functions is basically this. Okay. So, this is the functions. Okay. So, I define the functions as a functions of small t and capital T, right, and this is the standard way to define in Mathematica, okay, and this is basically minus k times t minus t environment, right. So, this is the functions here, right. So, if you compare this to this, okay. So, you see the right hand side is the functions. So, I define these functions, okay, and then I define the Euler methods, okay. So, so this is the generalizing Euler method. So, I define. So, this is, so once you know the functions and the initial conditions. So, the first argument is f, the function, and the second argument is the initial conditions y naught. So, in this case this is t. So, t naught, right. So, this is t naught, okay, and then we know that the initial time to maximum time, t naught to t max, okay, and this is the time step, okay, h, right. So, these 4 arguments are there, okay, in Euler methods, okay, I define. Now, once you know this t naught and t max, let us say t naught to 0 and t max let us say 5, okay. So, then you calculate the t list, okay. So, this t list basically from t naught to t max in a step of h, okay. Small step is h, let us say h is 0.1, then basically in the 0.1 gap. So, you create a list, okay. So, that is t list, okay, from t0 to t max, and your n list, n steps, basically total number of steps. So, this is basically number of the length of t list, right. So, that is how many steps are there, okay. All are the same size with h, okay. So, h is a step size, and yeah. So, here I create a y list. So, that is basically because here I use y. So, that is why I put y list. So, this y list is basically constant array 0 n steps. So, that means I create a empty list, okay, where all the elements are 0, right. So, I create a list where all the elements are 0, okay. Now, I assign, let us say y naught. So, I assign to the first element in the list. So, this is basically y list, and double bracket, okay, third bracket is 1. So, that means the first element in the list where I assign y naught, right. Now, I performing a loop. So, this is do loop, okay. So, the in y list the other elements in the list are basically n plus 1 calculated from this, okay. So, if you know, so this is basically y list n and h plus f t list n on y list n. So, this is your formula, right. So, I just put it here. So, y list n plus 1 equals to y list n and plus h f functions of t and y. So, all are the list, okay. And I run. So, this is basically you see that. So, this is a number, okay. So, y list n plus 1 means that the n plus 1th element in the list, okay, and this is the nth element in the list, and h times f as a functions of 2 variables. So, where you see the t list n, again the nth element of the t list, and this is nth element of the y list, okay. And I run n from 1 to n step minus 1, okay, because n, if you use n step minus 1. So, that means once you plug it here, okay, so that actually assigned to your last argument, last element in the list, okay, n step. That is why I use n step minus 1, okay. So, if you put n step plus 1, so that means you have to create a list where the length of the list is not n steps, is basically n step plus 1, okay. Because I know my length of the list is n step, okay. right, the length of the T list. Okay. So, that is why I use n step minus 1, okay, because if we just put it in step minus 1 here. Okay. So, you see that actually assign your n step, because minus 1 plus 1 are cancelled. So, that actually assign to your last element in the list. Okay. And then I transpose the value. Okay. So, why I transpose, because so this transpose actually what this transpose tell us. So, you can cross check with that. So, let us say I have a T list, where you see that T list are basically some 0, 0 0.1, 0 0.2, 0 0.3, right. So, let us say 0 to 0 0.3 with a time with a step size 0 0.1. So, we can create a T list, something like that. Okay. And your Y list accordingly, let us say this. So, you assign this, okay, and then you once you put this T list Y list. So, this is basically the result is something like this. Okay. So, your first T list and then comma and then Y list. Okay. But I have to collect one values of T and one values of Y. Okay. So, that is actually, so this is basically your two, yeah. So, this is basically your, let us say, 2 column. Okay. So, one is the T column and another is the Y column. Okay. So, it is basically let us say 2 cross n matrix. So, here this is basically 4. So, 4 cross 2 matrix, right. So, I have to convert it into a 4 cross 2 matrix, right. So, basically I transpose this. Once you transpose this, so you see you first collect one values of T, one values of Y, 0, 1, right, and then comma, and then you collect 0.1, one values of T, one values of Y correspondingly, right. So, this is basically 0.1 comma 0.82, that like. So, this is basically you just transposing the matrix, right. So, in this case your matrix is 4 cross 2 matrix, but you just transpose is basically 2 cross 4 matrix. So, that is I need, because I need for what is the values of Y, okay, where the T is this. Okay. Let us say T is 0, right. So, I know at T equals to 0 what is the values of Y. I know at T equals to 0.1 what is the values of 0.82, right, from this. Okay. So, the first argument tells you that, okay, if at T equals to 0, Y equals to 1, at T equals to 0.1, Y equals to 0.82 in this way, right. So, such that I can extract the things, okay, very quickly, okay, from this data pattern. Okay. So, that is why I transpose this such that your result are in this form. Okay. So, these functions Euler methods, okay, gives you the result in this format. Okay. So, that is actually helpful to extract the information. Okay. So, that is why I call this Euler method. Okay. So, now I solve this. Okay. So, already I assigned the functions f here. Okay. So, that is I assigned, and I also assign the values, okay, of the constant. So, then I just call this Euler method with these functions f and my, so in the place of y naught I put t naught, okay, because t naught in my case the t naught is the initial condition, initial temperatures, and yeah. So, within the second bracket I have to put initial time to final time, t naught to t max. So, I have put 0 to 20 and my time step is h 0.5. Okay. So, I put h 0.5. So, once you do this, so you see that the solutions Euler is basically give you the result, okay, in this format. Okay. Okay, let me check. So, you just put this, you see. So, at t equals to 0 your temperature 90, and then at t equals to 0.5 your temperature 80.25 and so on. Okay. So, in this way up to 20, so at t equals to 20 your temperature is 25.0976. Okay. So, at any intermediate step if you want to calculate, let us say you want to calculate at what is the temperatures at t equals to 9. Right. So, you can see at t equals to 9 your temperature is 28.487 using Euler method. Right. So, use the Euler methods, that is the first order approximations. So, using these methods you calculate what is the temperatures at a given time. Okay. So, now you can also plot. Okay. So, the T exact I assign the T exact. So, T exact is basically this one, the exact solutions of these equations. So, I assign this here. So, the T exact is basically the T environment plus T naught minus T environments and this. So, this is your T exact at a particular time T. So, now I plot here the two things. One is the solutions from using the Euler method. Right. So, this is my solutions Euler, okay, and other one is the T exact. Okay. So, here list line plot means that, so you see that these are the points, right. So, at t equals to 0 this point, at t equals to 0.5 some point. Okay. Now, I connected those points, okay. That is why I call list line plot. Okay. So, list line plot basically connected the dots, okay, and draw a smooth curve, okay, because these are the discrete point here. Okay. So, I call this, and now I have two things. One is the solutions Euler, this is basically these points, and another is that I created table, because this is a table, right. So, you can see that your 0, 90, 0.5, 80.25. Okay. So, this is basically a table. So, I can also create a table for from this. So, you just use the same thing again. So, t equals to 0 to 20 with a gap of 0.1, and I create a table where this is basically t and the values of this, okay, t exact. Okay. And now I compare with these values to these values, okay, the second argument. Okay. So, you can plot this. So, the plot looks like this. Okay. So, you can see that your red one is the Euler and the blue one is exact. Okay. So, they predicted well in this regime, okay. They predicted well in the later regime, but where the curve things are there is happen, right. So, there the predictions are different, right. So, that means the linear approximation is not good, okay, in this regime, okay, where the curvature is large. Okay. If it is a flat, or so if the functions are flat dependence, if the temperature is flat dependence on the times in this regime, okay. So, then there is a not significant changes, okay, using the exact and the Euler. Okay. The faster approximations is very good, okay, in this case, in this regime, okay, the later time regime, right. But in the meantime regime, so you see that the 1 to 5, 1 to 10, let's. Okay. So, in this regime, your Euler method is not good. So, you can also calculate the error, right. So, you can also calculate the error. So, this is your the solutions Euler, okay, and I just extract the second one. So, this is basically 90, 80.25, okay, and I add all these things and then divided by n. Okay. So, that is basically this, okay. The absolute values of, first I collect these numbers, okay, 90, 80.25, and I subtract with the exact values. Okay. So, this is my exact values, okay. If you created tables, okay, that gives you exact value from these equations. Okay. So, if you know what is the time, and then you can calculate the exact value at that time, okay, right. So, that is why so I calculate this t exact, okay. So, this is basically map to, okay, in the previous class, maybe previous to previous class we discussed. So, this symbol is basically map symbol, okay, right. So, it is a map symbol, and I calculate this t exact, okay, at the values of the first argument of this solutions Euler, right. The second argument is basically gives you the temperatures, and the first argument gives you the time, right, 0, 0.5, 1, 1.5. So, at those times I also calculate the values of t from exact formula, and here is the solutions from the Euler method, right, and I subtract those two values, okay, at each time stamp, okay. and then I calculate the mean of this. Okay, and first I calculate the absolute values of this, and then I calculate mean. Okay, so that is basically the error. Okay, absolute errors. Okay, so the global errors. Okay, the mean values of the global errors. Okay, so you see the error is large, 0.8 around. Okay. Yeah, any questions? So, here the operator is this is basically means the map. Okay. So, you calculate this t exact at the time is basically given by the first argument of this solutions Euler 0, 0.5, and then you want to calculate both things at the same time. Okay. So, this is you calculate the t exact at t equals to 0, and you calculate the so the solutions from the Euler method, the solutions Euler. So, this one, okay, and then you compare, and you can calculate at every time stamp, and then you then you take a absolute values and then mean. Okay. So, mean is basically sum over n divided by n, okay, divided over n. Okay, if there is a n points. So, in this case how many points? I have a 20 points, right. So, basically 20 points 0 to 20. So, 21 points. So, divided by 21. Okay. No, I have a time step is 0.5. So, it is double. Okay. So, it is 40 points. So, okay. So, so you divided by 40 here. Okay. And you can also calculate manually and then check. Okay. But you can also call mean. Okay. So, now I have to plot. So, I consider different values of h. So, here I choose h equals to 0.5, but now I take let us say h equals to 1, 0.5, 0.2, 0.1. Okay. The 4 values of h I call, and I calculate the error, okay, for each values of h. Right. So, you can calculate the error in this way. So, let us make a table for this h. Okay. So, first you calculate so for a given age you calculate the solutions using Euler method. So, you just call this Euler method and functions t naught and again 0 to 20 and h, because now I take different values of h. Okay. And you also calculate, so once you calculate these solutions, okay, so you can then calculate the mean values. Okay. So, you use the mean, again use the same formula, okay, but here you just use solutions Euler instead of you use solve. Okay. And again the second arguments, call the second arguments, and then t exact at the rate the first arguments. Okay. So, map to first arguments, and where the age is basically taken the age values. Okay. So, this is your age values is a list. So, they call one at a time. So, first call age equals to 1, and then call age equals to 0.5, and then call age equals to 0.2, and then call age equals to 0.1. Okay. Take one by one, they calculate the error. Okay. So, this errors is again is a list. Okay. So, you just check. So, this gives you a list, okay, and this is your age value list. Now, you plot. So, I plot in the log plot. Okay. So, where you see that they are basically proportionals. Okay. So, if age is increases, your error is also increases. Okay. So, mean global error is increases. Okay. And the almost the ratio is very close to 1. Okay. It is not exactly 1. You see that this is basically when age is 0.1, error is also almost 0.1, some slightly higher than 0.1, but if your error is if your age is 0.2, then your error is 0.3. So, this is a log plot. So, this is 0.2 and this one is 0.3, 0.4 and 0.5, 0.6. Yes, so it is a log plot, and you see. So, if age equals to 0.2, your error is 0.3. If your age is 0.5, then error is 0.7 or around 0.8. Okay. So, it is very close to 1, but you see that the trend is basically if age is increases, your error is also increases, okay, and almost proportionality, right, and that is actually in the Euler method. So, if you know that your global error is basically order of age, okay, is proportional to age, okay, because this is a first order approximation, okay, and that is why your error is basically proportional to age. Okay. So, if you increase if you so rather I am saying that if you decreasing your step size, okay, so age values, okay, then your error is small. Okay. So, now yeah, so far any questions? Okay. So, if not, so next I will solve the same problem using some improved Euler method. Okay. So, how to improve this method? Okay. So, you see there is a difference, right. So, you calculate using Euler methods, and the blue one is the exact, okay, and you see the differences. Okay. So, you are not getting correct results. Okay. Let us say if you calculate at t equals to 5, you are getting different results, okay, and that is very different. Okay. So, that means at this point your linear approximations is not good. Okay. So, you have to go beyond that. Okay. So, this is the RK2, the Ranjekutta 2 methods, okay, or the midpoint methods. Okay. So, that is the improved Euler method. Okay. So, Euler method is often inaccurate because it only uses the slope at the beginning of the intervals, and that is constantly used, okay, at every step, right. So, that is the problem. So, in the Euler methods we use the linear approximations and we calculate the slope at the beginning, and we use those slopes at every steps, right. Okay. But the RK2 and the midpoint method is improved on this by taking a trial step at the midpoint. Okay. So, we calculate the slope at the beginning, and then we check this at the middle of the time stamp, okay, and then calculate the again things. Okay. So, and taking the interstep for that slope. So, basically at the middle I calculate again the slope and check with the actual values, and then I update, okay, and then that actually calculate the later steps and using the I mean, so taking that entire steps using that slope. Okay. So, is this clear? So, first I calculate at the beginning the slope, then I update at the middle, okay, and I use this updated slope for the later part. Okay. While in Euler methods I calculate the slope at the beginning and I use throughout the process. Okay. So, that is why I wrote the constant slope. Okay. So, slope is constant. So, once I update this I use those repeatedly. Okay. I am not updating the slope again and again. Okay. Okay. But in this case I just in the improved Euler or on the Runge-Gupta methods. Okay. So, I update the slope at the midpoint, okay, and then I use the updated slope after that. So, basically the method is, so if first I calculate the functions, okay, f y n t n, okay, the nth at the nth point. So, this is k 1 and I update the timestamp is basically t n plus h. So, this is the definitions of age. How do I define the age is basically t n plus 1 minus t n, okay, the gap, okay, and this is constant. Okay. So, age is constant, the difference between these two, and I update y n plus 1 is basically from y n using this way. So, I calculate first so y n plus 1 equals to y n plus h times f of t n plus h by 2. At midpoint I calculate this, and y n plus h by 2 k 1. So, k 1 is basically this, right. So, you see, so initially you calculate this in the Euler method. So, you calculate y n plus 1 from this, but I use this here. So, y n plus h by 2 k 1. So, that means I calculate this at midpoint, right. So, you see. So, let us say y n plus 1 equals to y n plus h times f of t n. So, if you calculate at midpoint, so that means your y n plus h by 2 f of y n t n. So, it is y n plus h by 2 h over 2, and this is basically f of y n t n. I calculate at the midpoint, and I also calculate the time at the midpoint. Okay. So, this is basically t n plus h by 2, right, and then I use those things to update the next one. Right. So, from nth to first go to half step, and then you calculate the full step y n plus 1. Okay. So, that is the procedure we improved, okay, in the Runge-Gupta 2 method. Okay. So, RK2 method, okay. And that this gives you a second order accuracy. Okay. So, your global error now order of E square. Okay. In Euler method, the global error is order of H, and the local error is order of H square, right. But in this case, your global error is order of H square, and the local error is order of H cube, because you can see that this is basically order of H square, and your error is order of H cube, that is locally in each steps. Once you calculate globally, so that is basically multiplies times H. Okay. So, so it basically your global error order of H squares, because your each difference in the t n plus 1 minus t m is proportional to H. Okay. So, that is why once you calculate globally, so basically sum over all and then divided by these differences. So, this is basically H. So, that H actually cancel. So, order of H squares is remains in the global picture. Okay. So, that is why the global error is always 1 H less order in from the local error. Okay. Yeah. So, let us implement this in Mathematica. So, similarly for in the case of Euler method. So, here I define a functions RK2, where again same thing. So, I first my first argument in the f, and the second one is the y naught. So, f y naught, and then t naught to t max, and then h. Okay. So, I just update these things. Okay. So, inside the do loop. Okay. How to update your n plus 1 from n, right. So, that is the main point. Okay. It changes here. Okay. So, that is why the remaining things are the same, okay, that I discussed before. So, your t list is basically t naught to t max, okay, within a time with step size h, okay, and your n step is length of t list, and this is the y list. I first create a constant y list where all the elements are 0, and then I update the. So, I assign y naught to the first element, and then I perform a loop to update all other element in the list. Okay. So, once you know your t list, so first one is the t naught, and y list one is y naught. So, you calculate this, because I already assigned functions in the beginning. So, once you know the functions, you can calculate the k 1 and use those k 1, okay, to calculate y list n plus 1, the second element in the list, okay. And you do repeatedly, okay, the same things, okay, until n step minus 1. So, that gives you the last element in the list. Okay. and again we transpose those listed to extract so to extract the solutions in this form. Okay. So, in this form, so instead of this, so that is why I use transpose. So, it is basically a column to row matrix, okay, which changes. So, that is the transpose operators do, okay, and I run this. So, that is why my RK2 is now defined. Now, I call this. Okay. So, again I use the same thing here. So, in the Euler you use Euler methods and your argument is f t naught 0 to 20 0.5. I also use same thing here. Okay. But now my functions are RK2 because I use method is as RK2. Okay. And the remaining things are same, and the solutions is basically solutions RK2. So, you see, so that also gives you in the same form as before, okay, but you see the numbers are different now. So, you just check at 0.5 the first step. Okay. So, the values of t is 80.25, okay, that gives you the Euler methods, but from RK2 you are getting 80.9813, right. And then if you compare, let us say at the next one at t equals to 1, your RK2 method gives 73.2139, okay, and your Euler method is giving 71.9625. So, 71.9625 and your Euler method gives 73.2139. So, you see almost 2 difference, okay, 2.0 difference. So, this is 71 and this is 73. Okay. And that is actually, so if you see your Euler predictions is somehow smaller than your actual values. Okay. So, your actual one is the blue and the Euler one is the red, okay, is in red. So, that is why you see your if you use RK2 method, they are actually pulling the curve, okay, towards the actual values. Okay. So, you can see from this, let us say at 5. So, you see the differences is huge, right, from the blue one to red one, right, at t equals to 5. Okay. Let us check what is the number at t equals to 5. So, at t equals to 5 your Euler predictions is 37.7968, right, that is from the Euler method, right. Okay. So, let us first call this and run it here. Okay. Sorry. Yeah. So, now good. So, at t equals to 5, so your Euler method gives 37, and you see at t equals to 5 this is 39. Okay. You see the differences, right, and again your 5.5 point again 35 your from the Euler methods, but you using RK2 method is 37. So, that means this RK2 curve is somehow predict better than Euler, okay, because your actual values is close to this. Okay. So, you see actual value is higher than your Euler things and RK2 is also higher than your Euler things, okay, almost 2.0. Okay. So, now I plot this. Okay. So, let us say now I plot from the RK2 results the solutions RK2 and the exact one. Okay. Similarly, as before, so I created tables for the different values of time and I join this plot, okay, using a straight line. So, that is why I call list line plot. And other one is the basically from the RK2. Okay. So, from this data point. So, now if you plot this, so you see here. So, this is your red one and from the RK2 and the blue one is the exact blue dotted line, dashed line. Okay. So, you see it is almost overlap, right. So, there is a very little differences, but you almost overlap. Okay. Almost your dotted blue lines, sorry, dashed blue lines is overlap with the red ones. Right. So, you compare these two things. Okay. So, one is this and another is from Euler. So, from Euler you will just use solutions Euler. So, you see, yeah. So, I just change the name. So, this is Euler, right. So, you see the differences. Okay. So, it is almost overlap, but here are the differences. Okay. So, if you draw a fine curve, so this will be this. Okay. If you zoom this, okay. So, you see the differences in case of Euler, but in case of RK2 you see is almost overlap. Okay. So, that is why your RK2 method is somehow exact. Okay. Give a better predictions than the Euler. So, yeah. So, this is also again the same thing. So, I just plot Euler versus RK2 and this is the improvements. So, you see your RK2 is better than the Euler's, okay, and that is exactly match with this, okay, to the exact one. Okay. Okay. So, the results is basically the Euler deviates more from the actual values, okay, while the RK2 is almost overlap and or the significantly closer to the actual values. Okay. So, if you also calculate the error, okay, similarly as we do in the case of Euler methods, right. So, you calculate the error here. So, you calculate the error, right, using Euler case. So, this is basically 0.8. Okay. But if you calculate the same way, if you calculate the error in the same way, so first I call from the RK2. So, now my solutions are basically solutions from RK2 and this is the T exact, okay, and I calculate again the exact values at the time the first argument of these solutions and the second one it gives the temperatures and this is also gives you the exact temperatures, okay, at those times. Okay. So, if you calculate the errors, so you see in this case the error is 0.0437, while in case of Euler, okay, so I can call it here. So, it is basically 0.8. Okay. So, now if you see, so if this is proportional to h, so now it square it. So, if you square this, so this is basically 0.06, right. So, this is 0.04. So, almost same order, right. So, that means the global error in RK2 order of h square, okay, while the global error in Euler is order of h, okay, while the global error in Euler methods is order of h. Okay. So, that has become clear. Any question? Okay. So, this is the, I mean, we actually discuss in details that how if you improve your Euler methods, okay, so you reduce the error, okay, and also this is, so reduce the error means that your predictions is very closer to the actual values. Okay. So, this is, so I choose this example such that where we know the exact solutions and I compare it, okay. But in some cases we do not know the exact solutions, right. So, we actually solve numerically, right. So, in that case, so we do not know which method is good because there is no exact result to compare with this, okay, right. So, here because you know the T exact, that is why you compare and you calculate the errors, right. But if you do not know the actual results, the exact analytical solutions, okay, then how do you compare? Okay. So, these are the methods to tells you that that which one is good or which one is bad. Okay. So, let us do one more examples. Okay. Okay, let us see. Okay, so in this case, so I choose an example where a vertically falling object, so you know, let us say the falling under gravity, okay, falling object under gravity, okay, and there is a no drag force, but now I use a drag force, okay, where the drag force is basically from air, okay, and that is quadratic, right. So, if we include those quadratic drag force from air, okay, so then the equations is basically if I mean F equals to ma, it changes, right. So, that not follow your Newton's law, because there is a drag force. Okay. So, now your force is dvdt, okay, I choose mass is 1, okay. I mean if you divide it by mass, okay, so this is yeah, so dvdt equals to g minus c over m. So, this is a constant, okay, drag coefficient, okay, better to say drag coefficients, and this is your velocity, and now mod v, okay, right. So, this is my drag force, okay, v times mod v, okay, is actually quadratic, but with a proper magnitude. So, sign is also different that, and yeah, my initial conditions are t equals to 0, v equals to 0. So, initially at rest, then I dropped in the medium where the drag force is quadratic. Okay. I want to solve this, okay, problem, and yeah. So, using RK2 methods, okay, that I discussed in the beginning. So, let us see. Okay. So, my initial condition is this. So, first I assign the values of the constants. So, in these problems, how many constants are there? 3 constants, right. So, one is g, another is c, another is m, the drag coefficient, mass, and the gravity, okay, gravitational constant g. Okay. So, I put all these values in SI units. So, this is basically g is 9.8 and m is 1 and c 1.2. Okay. And I also know what is my function. So, my functions is basically this, okay, whatever in the right hand side of the equation. So, your functions is basically g minus c over m, v times absolute values of v. Okay. So, it is a mod v. Okay. So, we call by these functions absolute values of v. So, I assign this. So, you can solve this equation. So, now your equations is basically dv over dt. Okay. So, this is basically v prime t. So, v prime t means that the first derivative with respect to this argument. Okay. So, here the argument is t. So, v prime t, it means that it derivative v with respect to this argument. So, if you put here x, that derivative with respect to x. So, here I put t, that means its derivative with respect to t. Okay. And which is equals to, so here this is a equal equation. So, that is why I put double equals. Okay. If you use single equal, that means is assigned. Okay. So, you will see I use a single equal, that means I assign 9.8 to the variable g. This is not an equation. Okay. So, here I assign 1 to m, that is why I use single equations. If you use double equations, that means this is a equations, okay, where I solve left hand side and right hand sides, okay, and I calculate, I extract the solutions. So, I am not assigning. Okay. So, my equations is basically now g minus c over m times v t times absolutes of v t with the initial conditions v 0, v at t equals to 0. So, that means your functions is v t. So, at t equals to 0, you put 0 instead of t, and this is v. So, that actually 0. Okay. Again, this is an equation. So, and we solve v, right, and from t to 10, okay, t equals to 0 to 10. Okay. So, this is the V exact, I use ND solve to solve this. Okay. So, this is a first order differential equations you can solve. So, this is basically numerically. So, N stand for numerical and D solve differential equations solve. Okay. So, this is the functions numerically solve. Okay. This is not an analytical. So, that so the result gives you a numerical number, okay, not an analytical expressions. Okay. If you put D solve, that gives you analytical solutions, but most of the cases analytical solutions is not exist. So, you just calculate numerical values. So, you use ND solve, okay, instead of D solve. Okay. So, I calculate numerically, okay, to solve this equation. So, I use ND solve, okay, and that gives you this. Okay. So, you can check the output is basically, so it is interpolating functions numerically. Okay. So, then you have to calculate once you know what is the time, okay, they interpolate to that values, okay, to gives you the values of V. Okay. Right. So, that means the ND solve actually solve some discrete points, okay, and then they interpolate. Okay. So, if you want to know, let us say at t equals to 5, what is the values of V? From these interpolations, they gives you that this is the values of V. That is why the ND solve works. Okay. And you can use RK2 method to solve this, okay, these equations. So, again I call RK2 that I defined here, right. So, the argument is f y naught and then t naught to t max and then time step h. So, I call this. So, my RK2 and the functions I already defined here. Okay. So, f and then the initial value. So, initial value is 0, you see V naught is 0 at t equals to 0. So, this is 0 and yeah, and t naught to t max. So, again I choose t naught 0 and t max 10 and h value I choose 0.2. Okay. So, I choose h value 0.2 and the solutions is I assign solutions RK2. Okay. Now, I plot V exact and solutions RK2 similarly as before. Okay. So, solutions RK2 and I create a table TVT, okay, at V exact 1. Right. So, you see V exact 1 is basically time and then the value. So, at each values of t, okay, I calculate V exact Vt, right. So, I calculate Vt for each values of time. Okay. So, so this is basically I calculate Vt where t is basically the first argument of V exact 1. Okay. So, basically we are using the same thing. So, t 0 to 10, in this case I also choose 0 to 10. So, I can calculate using this way, where your t is basically 0 to 10 with a time step of 0.05, right. So, the step size in this case is different, but I think so I am calculating I am plotting list line plot. So, they at the end, so they interpolate. Okay. So, you see. So, in this case your RK2 methods is not gives you the exact one. So, you see the exact one, this the teal color and the RK2 is the red color, right. So, you see the difference. So, that means in this problem again RK2 is not works, okay. It is not a good method. Okay. Right. So, your teal one is the exact and RK2 is the is in the red. Okay. So, apart from this higher curvature, so at this point the curvature is high, that is why this method fails. Okay. So, now go back to this. Okay. So, when we compare Euler to exact, okay, So, you see that the curvature is little higher, this method fails, the first order approximations fails. Now, I go to the second order approximation. So, basically I am going beyond Euler. Okay. Then this is perfectly fine, they can capture this kind of curvatures. Okay. Now, I am going to more curvature. Okay. So, now I am choosing a solution problem where the solutions basically in this pattern. Okay. So, it is basically rapidly fall after a certain time. Okay. So, this is basically is denoted as terminal velocity. Okay. After some time your velocity suddenly change, you see. So, at t equals to 1 is very close to 1, your velocity suddenly drop. Okay. So, that is the terminal velocity. So, in this case again the RK2 method fails. Okay. So, if you calculate the terminal velocity from RK2 and you calculate the terminal velocity from exact solutions. Okay. So, you are getting very different. Okay. The predictions of terminal velocity in the RK2 it is not correct, right, if you compare with the exact one. Right. So, your RK2 slightly overshoot the terminal velocity because of the non-linearity things. So, I have a non-linear quadratic diagram introduce the curvatures. Okay. So, in the previous case my equations are very simple, okay, it is a linear equations. Okay. In this case RK2 I mean agree very well with the exact one. Okay. So, if you see this one, so your RK2 very well with the exact one, but now if we introduce some non-linear things into the problem, then the RK2 method is not good because of these non-linear things. Okay, introduce curvature that changes rapidly when the velocity grow. Okay. So, you see if you increase the velocity, okay, your curvature changes rapidly at some point. Okay. In that case RK2 is fails. So, what is the next? Yeah. So, before I am going to the next, so is there any problem or is there any question? No question? Okay. So, if not, then I will move to another methods. So, that is one order again improved. Okay. So, now I am going to the fourth order method. Okay. So, Ranche-Kutta fourth order method RK4. So, in this case I update the slope at many times. Okay. So, first I update the slope at the midpoint similarly as before. Okay. So, I update the slope at midpoint and then again I update the slope at that point. Okay. So, that means I update the slope at midpoint 2 times. Okay. So, first I calculate the functions at t and y n, use those I update this at midpoint to k 2, use those I update this again. So, this is k 3 and at the final I calculate k 4 using this. Okay, at the end. and then I calculate y n plus 1 is basically sum over all these things in this particular pattern. So, basically 4 sampler slopes. So, I calculate in, so while the Euler methods I only use the slope at the beginning. In the RK2 methods I calculate the slope at the beginning and then I update at the midpoint, and then I use those slopes at the later part. Okay. But while the RK4 I take 4 different sample of slopes, so K1 through K4. First I calculate this in the beginning K1, and then I update this K2, I use those, again I update this K3, and at the end I update K4. Okay. And I consider all of these slopes and take 1 over 6. Okay. So, this is the particular pattern of this method to update y n plus 1. Right. So, across the interval h I calculate 4 different slopes to update y n plus 1. Right. So, you see the differences. In Euler method I just use 1 h, right. We across the interval h I calculate only one slope, and that is constant every intervals, right, over the time. So, in RK2 I use 2 slope, okay, across the interval. One is in the beginning, another is the midpoint. While in RK4 I use 4 different sample of slopes. One is the beginning, another is the midpoint. I use same thing again at the midpoint. I calculate the another slope, and then I calculate at the end h. So, basically across the interval h I calculate 4 different slope, and then I calculate the weighted average of these 4 slopes. Okay. So, you see 1 is the beginnings, and 2 times is the middle, and again 2 times is the middles, and again 1 is the beginning. So, 2 to 4 and then 1 6. So, I divided by 6. So, this is the weighted average. So, I put weight to each slopes different. Okay. So, in the beginning slope I put weight 1 over 6, in the middle slope I put weighted 2 over 6. So, there is a 2 middle slopes. So, that is why the total is 4 over 6, and again I put the weighted at the end is 1 over 6. So, it is different weight at different slope. Okay. So, that is the weighted average in these methods. Let us see what this method gives. Okay. So, we choose the same problem, this quadratic drag force problem, okay, that I consider here, because in this case the RK2 method fails. Okay. So, let us use RK4 to solve this. Okay. So, let us first define RK4 again the same way as we did before, right, in case of RK2. So, again in this RK4 I again put the arguments are f, y naught. So, your functions, and this is the initial values, and then t naught to t max, and this is the timestamp h. Okay. So, then we create a module. So, first I have to assign what are the variables inside this function. So, you have to assign within this second bracket. So, in this case your variables are t list, that is basically the list of t naught to t max with a timestamp, okay, that is h, and you have to create a y list, that is empty list, and then we have to assign the element of the list using this loop, and there are other variables like n step, okay, the total steps of this. So, total steps, so this is basically length of your t list, and how many points are there, okay, or elements in the list are there, okay, how many elements are there, and this is k1 to k4 are the 4 slopes, okay, you calculate. Okay. So, that is why you have to put this in the modules, what are the variables, and then I performing a loop to update the element in the list. So, initially I start all the elements in the list at 0, okay, 0 to n. So, this is basically constant arrow 0, and there are n steps. So, this is basically we create an empty list, okay, with all elements are 0, okay, that is the empty list, okay. And the length of list is in step, okay, in steps. Okay. So, first I calculate k 1 and then I use this to calculate k 2. Okay. So, you just use this formula. So, k 1 is f of y and t n. So, k 1 is basically f of t list n, y list n, and then we calculate k 2. This is again the functions of t list n plus h by 2 and y list n plus h by 2 k 1. Right. Now, if we use this k 2 to update this k 3, right. So, if you use k 2 to update the k 3 similarly as before, so we just f of t list n plus h by 2 comma y list n plus h by 2 k 2. And now, once you know k 1, k 2, k 3, so you can also calculate k 4 using k 3. So, yeah, so this is basically just h times k 3. So, y n plus h times k 3 and t list n plus h. So, now once you know k 1, k 2, k 3, k 4 now, so you can calculate y list n plus 1, okay, the next element in the list. So, if you know the first element in the list, okay, and this is basically the weighted average, you see h over 6 and then k 1 plus 2 k 2 plus 2 k 3. So, k 1 plus 2 k 2 plus 2 k 3 plus k 4, okay, and we perform the loop from n equals to 1 to n step minus 1. Okay. So, if you start with n equals to 1, okay, so this n 1, then you can calculate n 2, sorry, y list 2, because I know the first elements are the initial values, okay, y naught, okay, that is given, okay, because this is in the argument, okay, you have to given this the initial conditions, and then we solve this, okay. And at the end we transpose this list, okay, to get the desired form of the solutions. So, now I do a numerical solutions of this, right. Yeah, any questions from these implementations of the RK4 method? Okay. So, if not, so now I solve these equations using RK4 method, right. So, I solve which equations? These equations, right, where my functions is basically g minus c over m v by v. So, here I assign the functions f. So, that is why I use the same functions here. Okay. Whenever you call f, that means that actually call the last one, okay, where you last define the functions f. Okay. So, since after that I am not assigning to anywhere the f variables, okay, that is why so this actually uses here, okay, when you call f, okay. And again your initial condition is 0, because here my y is basically v, right. So, this is my v. So, v naught is 0, at t equals to 0, v naught is 0. So, that is why I put 0 here, and yeah. So, my time is initial 0 and the final is 10 with the time step 0.2. Okay. And then I plot list line plot, again the same before. So, from the RK4 and from the exact one, okay, as we did before. So, okay. So, now you see, so this is exactly overlap. Okay. So, the RK4 in this case is very good. Okay. So, you see, yeah. Okay. So, here some zigzag. So, that is why, because if you just increase your you decrease your interval, let us say I put 0.1, that actually better. Okay. So, now we see, So, this zigzag is also very smooth. Okay, now, because you know just in this case you are basically using very small gap, okay, between these 2 points. So, if you put a large gap, let us say 0.5, it's not good, right, because this is a sudden jump, okay, and you are choosing your steps is basically one from here, another from is there. So, they cannot predict it very well, right. So, in these higher curvature curves, okay, you have to choose a small let us say 0.3. So, you see still is not good, okay. So, you have to reduce the values, okay, 0.2, and you see, because I use 0.2 here as well, right. I also use 0.2 here, but this is not good. Okay. So, again if you use 0.2 in the case of RK4, so this is exactly good. So, now if you just check, okay, so let us say I reduce here 0.1. So, still there is a difference. So, right, because your error is proportional to h square. So, if you use large error, large values of h, okay, that means your RK2 is order of h square. Now, if you calculate what is the error in RK4, so RK4 is basically your global error order of h to the power 4. Okay. So, that is why given values of h, okay, let us say 0.2, that is very good for comparisons. Okay. So, you see the error is large here, but in this case if we h 0.2, so error is small here. Yeah, maybe some people's maybe join, let me check. Yeah, so let me share my screen again. Yeah, all right. So, since the error is large here, so in case of RK4, your error global error is order of h to the power 4, right. So, that is why given values of h 0.2, in case of RK4 is exactly overlap, almost overlap, okay. But in this case you see in case of RK2, so there is a difference, large error, okay. And this error actually small in case of RK4. Okay. Because the error is order of h to the power 4. Now, yeah, I will check this one, okay, also numerically, okay. So, if you just check 0.1, so you will see it is almost overlap, okay. But in case of RK2, it still differ, okay, slightly differ, okay. Okay. So, now we calculate let us say calculate the global error, okay, in RK4 and then compare with the RK2, okay. So, I use 0.2 for comparisons, right. So, in this case I use 0.2 and that is my solutions RK2 and this is my solutions RK4, okay. So, I calculate the error, okay. So, the solutions RK4 we have a two things, the first one is the time and the second one is the velocity. So, this is the t value and this is the velocity, okay. So, t value is 4 and velocity is 4 and then I calculate the exact value from this one, okay. This is gives you my exact value, okay, V t. So, that is why I just V has and then at the rate the first argument and I calculate this t values, okay. The time that is the same time I calculate, okay, where I calculate the velocities using RK2 method, okay. And then I calculate the error, okay, the absolute the difference between two things and then I calculate the mean, okay, the mean of this error. And I calculate the same thing in case of RK4 here. So, you see the difference. Okay. So, here the error in RK2 is 0.011, basically order of 10 to the power minus 2, but in this case you see the order of 10 to the power minus 4. Right. So, you see the difference, okay, the order of magnitude. Okay. Right. So, this is 10 to the power minus 2, right. So, the order of 10 to the power minus 2, because it changes at second digit, second decimal place. Here it changes at fourth decimal place. So, this is basically order of 10 to the power minus 4. So, now you see what is the error is in RK2 global error is basically order of h square, but in this case then the global error is order of h to the power 4, right. Because if this is h square and then we put a square, because this is 10 to the power minus 4. So, this is the global error in RK4 actually order of h to the power 4. Okay. So, it is clear that why the global error in RK4 is order of h to the power 4. So, that is why if you use small n small h, okay, your error is very small, okay, in case of RK4. Okay, all right. So, next I will discuss some problems, and that is related to your assignment problems. Okay. So, let us say first problem, consider the solving the initial value problem. So, this is basically dtt over x equals to minus 2 t x, where at initial condition at x equals to at x the values of x at t equals to 0 is 1, right. This is basically x 0 is 1. Okay. Use RK2 and RK4 method with the step size h equals to 0.2 and find the approximate values of x at t equals to 1. Okay. So, use two methods RK2 and RK4. So, it is very simple. First I assign the functions f of t x is minus 2 t x. Okay. So, this is minus 2 t x, and I assign, so first assign these, and the values of h 0.2 is given, okay, and RK2. So, I already defined the RK2 functions here. Yeah. So, here I just put the values of the arguments. Okay. So, I call this RK2 here. So, I call the RK2 here, the functions, now I update the functions. Okay. So, that means once you put it here f. So, this f basically previously defined. So, here I defined here, that is why this f actually call these functions minus 2 t x, and then my values are 1 at x equals to at t equals to 0, the values of x is the variable that I want to compute. So, that is why you know what is the initial values of x, initial means at t equals to 0. Okay. So, this is t equals to 0. Okay. So, and your final value 1, because I want to compute the values of x at t equals to 1. So, that is why I put 1 and with a step size 0.2. So, your h is 0.2 I already assigned. So, now I calculate this. Okay. So, that gives the result this. Okay. So, that means at t equals to 1. So, this is t equals to 1, and your so and your the values of x is basically 0.364379, right. So, that is the values of x at t equals to 1, because the solution store as this. So, t naught x naught, t 1 x 1 dot t 5 x 5, right. So, at given values of t, what is the values of x? Okay. So, that means in the questions it asks that find the values of approximate values of x 1. So, you just put things. So, this is the answer. So, So, at x equals to 1, this is the values of x. Similarly, we just extract this using this way. So, your solutions are K2. So, this is the solutions, and you extract second argument. Okay. So, this is the first argument and this is the second argument. So, this is the first argument, this is the second argument. So, we extract second argument, but from the last one. So, this is minus 1, that means the last one. Okay. So, from the at the end, what is the last? So, this one is the last. So, you put minus 1 and comma the second one, second argument, the second element in the list. This is basically return. So, once you call this, so this is return this one. So, now if you do if you solve this using RK4 method, right. So, again you call RK4 because RK4 I defined previously. So, you have to define previously, okay, before you calling this. So, I defined here RK4. Okay. So, again the arguments are the same. So, if 1 and 0, 1 and h. So, you call this, again the solution stored in this form. Okay. So, at t equals to 1, your value is, the values of x is basically 0.367904. So, you can extract again the same way. So, you see. So, you see the differences. Okay. So, here your RK2 method predict 0.364379 and your RK4 method is predict 0.367904. Okay. So, third digit the changes. So, for MCQs, okay, I mean, this is crucial, okay, because it changes at third decimal place. Okay. So, yeah, so any question? Okay, so now I solve another problems. So, this is again similar to your assignment problem, week 5 assignment problems. Yeah. So, let us now consider a second order ODE problem. So far I discussed first order problem, okay, now I discuss second order problem. Okay. So, let us consider simple harmonic oscillator. Okay. So, we know the simple harmonic oscillator is basically x double dot t. So, this is basically double dot means this is the derivative with respect to time. So, second derivative with respect to time. So, 1 dot means 1 derivative with respect to time, double dot 2 dot means the 2 derivative with respect to time. Okay. And this is basically equals to minus x. Okay. So, this is simple harmonic oscillator where oscillator where I choose values of m and k are 1 1. Okay. So, all of the constants are unity and my initial conditions. So, since it is a second order equation, so I need two initial conditions. One is the values of x at t equals to 0. So, this is 2, another is the velocity, okay, the derivative of x at t equals to 0. So, this is the x dot, okay, the derivative of x at t equals to 0 is 0. So, I need two initial conditions, one is the positions and the velocities in order to solve the second order equations. So, in order to solve first order equations, we need only one positions, because I solved the equations for v, but here you solve the equations, okay, where the two derivatives are there. So, that is why you need the x and the x dot, okay, in order to solve equations with x double dot. Okay. So, that is the basic things you have to know. Yeah. So, now we use the RK2 and RK4 method with the step size h.05 and find the approximate values of x5 and v5. Okay. So, in order to solve this, so similarly as before, but here we have a two derivatives, okay, second order equations. So, I can convert this into a first order equations, right. So, basically first order couple equations. So, you see I just use in a matrix form. So, d dt of x v equals to v minus x. So, this is a matrix. So, first I call that okay, my v is dx dt and dv dt is basically minus x. Right. So, here you see that this is basically x double dot. Okay. So, you calculate that okay, so d dt of dx dt, right. So, dx dt is v. So, that means dv dt equals to minus x. So, this is the second one. Okay. So, dv dt equals to minus x and dx dt equals to v. Okay. So, if you put this here, that actually gives you this, the first one. Okay. So, then this is a first order equation, sorry, right. So, now your functions is basically v and minus x. So, this is a matrix. So, your functions is a matrix, okay, and your variables are x v is a matrix form. Okay. So, that is why your variable is x v in a matrix form. So, your variable, let us say this one is a variable, okay, and this is the functions. Okay. So, that means this is basically dy dt equals to f. Okay. So, here I instead of y I put a variable, this is basically again a matrix form x comma v, and my functions again a matrix. So, v comma minus x, the right hand side. Okay. So, I assign this, and so my initial values are there, is again a matrix. Okay. So, initial values means that the initial values of x, initial values of v. I know initial values of x at t equals to 0, this is the initial values at 2, and v is basically x dot is 0. So, that is why my x naught are 2 comma 0. Okay. So, I basically solve all the things in a matrix form, okay. And I choose a is equals to 0.5 because here the a is equals to 0.5 is given. Okay. So, I choose this and I solve RK2 using RK2 method. Okay. So, you put RK2 or the function f is this, and your x naught is an array, okay, and the time is basically 0 to 5 and then age. Okay. So, you see now the solutions is given in this form. So, time comma x comma v. So, first one is time comma x comma v, and this is one thing. Okay. The next one again t. So, t is 0.5, x 1.75, v minus 1. Next t is 1, this is your x, this is your v. Okay. So, you have to calculate. So, the solution structure is basically t naught, x naught, v naught, t 1, x 1, v 1 within second bracket, because x 1, v 1 are basically written in a matrix form, okay, in an array. Okay. So, now if you extract, so from this you can just extract that what is the values of x 5, that means at t equals to 5 what is the values of x and what is the values of v. So, let us see at t equals to 5, so the last one. At t equals to 5 the values of x is this and the values of v is this. Right. So, you can also extract using this command. So, first we extract this one. Okay. So, the second, so this is the first one, this is the second element. Okay. Second element is an array. So, this is your last element in this array. So, you see there are too many arrays. Okay. So, within this is the last one. So, that is why minus 1 comma the second one is this, okay, second element. So, once you call this minus 1 comma 2, that return you this. Okay. So, this is an array. Previously you see they return a number because there is a 2 array, 1 and there is a 2, right. So, once you call minus 1, so minus 1 it means this and comma 2 the second one. So, this is a number, right, that is why they return number. But here this is the minus 1, the last one, and 2 is basically this one. So, this is an array. So, that is why they return array, right. So, the array of x 5 and v 5. Okay. Okay. So, this is the solution. So, or you can also do other way. So, you first transpose these and then, so here what I did. So, first I, in order to extract the x solution, mainly the first one. Okay. So, I have to know that at what values of t. So, first extract t and then the first one this. Okay. So, that means I create a table t comma x. Okay. So, this is the first one from all the data sets, all the sets I extract the first one, that means the t, and I extract the second one with the first one. So, comma 2 comma 1, because second one is an array. So, I extract from this 2 the first one, that is why this one. Okay. So, there are 3 commas. Okay. And that returns, okay, so 0 comma 2 and then 0 comma 0.5, the second one 0.5 comma 1.75, because you extract the first one. So, and then the x solutions at t equals to 5, that means the last one. You just call again for these things, you call minus 1 comma 2 from this array x all, okay, from this array. Okay. Now, you call minus 1 comma 2, that gives you this value. Okay. That is exactly the x values. Similarly, for v. So, for v case same thing, similar to this, but here we just put this one is a 2, because you extract from second array this one, the second element. So, just put 2 here. Okay. This is a v solve, and from this again we call this from v solve. So, this is an array of array. Okay. Now, we extract the last one of minus 1 comma 2, that gives you 1.91791. Okay. Okay. Any question? Okay. So, you can solve damped harmonic oscillator using this RK4 and RK2 methods. So, using this technique. Okay. So, here I just discussed that how to solve second order equations, okay, using this matrix form. So, this matrix form is basically first order equations, right. So, you can also reverse these equations, the damped harmonic oscillator, into a first order equations. Okay. Couple of first order equations, okay. And there is this matrix form, and you can easily solve this, okay, using those technique, okay, that I discussed so far. So, that is your exercise. So, I can do the similar things for LCS circuit. Okay. So, this is exactly similar to the damped harmonic oscillator, you will see. So, your M is L and gamma is R, and K is basically 1 over C naught. Okay. And in this case the displacement y, in this case the charge q, okay, of the capacitor, and it is functions of time. So, I convert into a first order equations into a matrix form. So, d dt of q dot. So, in this case I choose x v. So, v is basically x dot. Okay. So, you see d dt of x. So, you can also write x dot here. So, q dot and dq dt is basically q dot, and dq dot dt basically this one. Okay. So, dq dot dt means that the second derivative, so that equals to minus r over L. So, minus r over L q dot minus 1 over L C naught q, right. Okay. So, this is the form. Now, I have to solve this. This is exactly this. Okay. So, if you put this, so your functions, then f is basically again a matrix. So, first I assign the values of this constant L, C and R naught, 3 constants are there, L, R and C naught. Okay. So, I assign some values. Sorry. And my initial conditions q naught again. So, this is in q dot. Okay. So, I have to put the values of q and q dot. Okay. So, this is my initial conditions. So, it is an array from, and the functions are basically q2. Okay. So, here I assign q2 is basically q dot, okay, and q1 is basically q. Okay. So, you can assign in a matrix from an array, okay, this, and then you call RK2 to solve this. So, you can easily solve as is before, and yeah. So, now if we extract the q RK2, that means the first one. So, basically yeah. So, time. So, this is the time, and this is from the second array the first element, that is q. Okay. So, this is basically a, so this is time and the values of q, time, values of q. Okay. So, at each time what is the values of q, okay, that returns. Okay. So, this is exactly same this one, at each time what is the values of x, okay, and this is return at each time what is the values of v. Similarly, you can also extract q dot, but I am not extracting q dot. So, I just only extract q, okay. That is why I put 1 here. You can also extract q dot. Okay. So, now I calculate 3 quantities. One is the omega naught 1 over L c square root of, and gamma r over 2 L, and omega d. So, these 3 quantities. So, if you just compare with this, okay. So, this gamma. So, here I also define some gamma r over 2 L, okay, somewhere. So, if you define this, and then you can also know what is the exact solutions of these equations. So, this is the exact solutions, e to the power minus gamma t times cos omega dt, where gamma is basically r over 2 L, okay, and cosine omega dt, omega d is basically this, okay, omega naught square gamma square. So, this is the exact solutions. Okay. Now, you plot. Okay. So, if you plot this, so if you plot this, so this is from RK2, and this is the exact one. Okay. Similarly, as before. So, if you plot this, so you see there is a difference. So, initially they predicted very well, but as the time goes on, okay, your exact one is very different from the RK2 method. Okay. RK2 in red and exact one is teal. Okay. So, now you do the same thing using RK4 method. So, I just call RK4, I defined above, okay, and then I extract q again similarly as before, and I can plot this. So, you see RK4 is predicted very well with the exact one, okay, with a very small error throughout the time. Okay. Right. So, if you see the comparisons, so RK4 is very good, okay, if there is a too many curvatures. Okay. So, you can also think that how the values of q naught, so, and you can also calculate the error. So, in RK2 the error is 0.03, but in RK4 the error is very small, 0.016, okay, almost half. Okay. Yeah. So, any questions? So, next day I will discuss some another example. So, the van der Pol oscillator. So, this is a little tricky, because in this case there are too many things are there. Okay. So, I will discuss in the next class. Okay. So, there are limit cycles, okay, and phase space. So, this is very non-linear problems. I will discuss these examples in the next class, but yeah. So, so far any questions? Otherwise, I will stop here. Yeah. Okay. So, if not, then I will stop here, and in the next class I will discuss, first I will discuss the van der Pol oscillators, nonlinear dynamics, okay, and how to solve using RK4 methods, and compare the solutions with the exact one. Okay, and then I will discuss some things that is from week 6. Okay. Okay, then See you. Bye bye.